Welcome you all. Today in this lecture I just overview what about the time response. So time response. Now for time response we can divide time response into two categories. I told you that. So we can say that we have first order, we have second order. So now these are the basic categories where we discuss the time response. Now after the higher order response we actually approximate using the second order response. So main thing here is in first order response you have you can change the parameter that can only increase or decrease the speed of the response, but in second order if you change the parameter this will also affect the shape of the response. So this is very important to understand how shape related with the response. So let me start with first order response, how first order look like and what type of information we can get from first order response. So if we look at the transfer function first, so first order response we can write the transfer function of first order as s plus a. So this is first order system. So the main idea here is that if we look at the plot of this first order system, t is the time, so it will start and try to reach. Okay. So assume this is 1 here. So this is the output to the step input if we give step input to the system. Okay. Now if how this response look like, so this y of t is actually equal to 1 minus exponential minus at. So this is the response. So this is first order response. So we have some parameters for first order. So first one is time constant. Okay, time constant. So time constant is represented by tau, is actually value of the time, or a time when we calculate when the value reach to the 63%. So if we make here, it is the, assume that this is the 0.63. So this time is known as time constant and represented by tau. Now this time constant is actually equal to reciprocal of pole location. Okay. The next thing is, so important is, next is rise time. We represented by TR for first order, and we say that this rise time actually equals to 2.2 divided by A. So rise time is, if I made here, it is, if this is the 0.1, if we reach somewhere here, so this time is rise time, TR. So this is the formula for rise time. And last one for first order is the settling time. We represent it as TS. So settling time is equal to 4 divided by A. So settling time is that when you reach within the 2%. So when you reach somewhere here, okay, if this value is around 0.98, so this time is known as settling time. So these are the information that we have for first order system. So if a time constant is given to you and you easily calculate the transfer function of the system. Now we move to next one, which is known as second order system. Now second order system has two poles, and we can write a generalized formulation for second order system, and that is equal to g of s is equal to omega n s square divided by s square plus 2 zeta omega n s plus omega n square. So don't forget s. I forget in previous slide, previous video lecture, so don't forget this s. Okay, so this is second order system. Now here important is this two things. One is zeta and other is omega n. So zeta is damping ratio, omega n is the natural frequency. Now we have some information here, so with respect to zeta and omega n. Okay, so if we say that zeta is equal to 0, we say that this is undamped. If we look at the response, so response is something like that. If zeta is equal to 1, we call it as a critical damped response. So this is critical damp. Now if we say that we have zeta, so for undamped, actually if I look at the pole location that are on the j omega axis here, so this is pole location, this is S plane. Similarly for critical damp, we have two poles that are on the left of plane, so on the same location. Now if we look at zeta that is greater than 1, we call it as overdamped. For overdamped response, if this is 1, you didn't reach the 1. So in that case you have some poles that are not repeating but on the real axis. So this is overdamped. Now the last one is that you have a response that is between 0 and 1, and it is known as underdamped. For underdamped response, what do you mean? Do you mean that you have overshoot? It will do something like this. If this is 1, so this type of, so this has happened when you have any pole here, complex poles. So this is behavior of second order with respect to pole location and with the zeta. Now second thing that we must know is about we have another information. So peak time, so we have peak time. We normally represented peak time with Tp, and we can say that this is equal to pi divided by omega n under root 1 minus zeta square. So this is, but remember this is only possible when zeta value is between 0 and 1 actually. Okay, so it is for underdamped. In overdamped you have to change the formula. Okay, so let me move to next page for other formulas. Then we have second order system. We discuss peak time, that is equal to pi divided by omega n 1 minus zeta square, and we say that this is only possible when zeta is between 0 and 1. Now the next formula that we can have is the overshoot. Okay, so for overshoot we have percentage overshoot, that is equal to exponential minus zeta pi divided by 1 minus zeta square times 100. So from this formula we can calculate the zeta. Zeta can be calculated using the overshoot as minus log of percentage overshoot divided by 100 and divided by under root, we have pi square plus log n square of percentage overshoot divided by 100. So this is the formula. We can calculate zeta from the overshoot. Now the third one important is the settling time, Ts. So Ts is equal to 4 divided by zeta omega n. Now the fourth one is the rise time. So rise time is not straightforward to calculate in second order system. So actually rise time has some extra information, that is it is from 10% to 90% of its final value. We call it as a range. So it is for overdamped system. Okay, so critical dam is formula a bit different, but if we look at the formula, so formula becomes pi minus theta divided by omega d, or in other words where theta is equal to tan inverse omega n 1 minus zeta square divided by, let me write on the next page. Okay, let me write this formula on the next page, it's better. So rise time is equal to pi minus theta divided by omega d, that can be written as pi minus theta is equal to tan inverse zeta omega n 1 minus zeta square divided by, now for omega d, instead of omega d write omega n under root 1 minus zeta square. So this is rise time. It will be workable when you have your overdamped response. Okay, now this what we know from the information that we have. Now then we discuss another thing, that is the dominant poles. These are those poles, if you have too many poles available in the system. So this is a higher order system, so The poles that are near to the origin is known as dominant poles, and they actually, because of slow convergence, they have the overall shape of the response. So this information is used when we have higher order system. Now the next thing is zeros. So how zeros behave? So there are two actually types. One is if zeros on the left half plane, then they didn't change much in the overall shape of the response. If away from the poles. So if they are left of, then they are also minimum phase system. So we have two types. One is the left half plane zeros, right half plane zeros. So for left half plane zeros, we call it as a minimum phase. What do you mean? Means that we have zeros lying here in S plane. We have negative value for 0. Okay. Non-minimum phase, we have 0 lie at the right side. So this is S plane. So this is non-minimum phase. So what happened in the response? If we have same system, it will behave like this for this 0. Okay. But for same system, if we put 0 on the right side, it will behave, it will start, go another direction and then come back. So this type of response is for non-minimum. So it is slow actually, sluggish response. So this is what we have about the knowledge of the response. And then we have another thing. So in time specifications that we will use for system analysis. In that case, what we have how system behaves. For example, this is j omega and this is real axis. This is my S plane. So we are talking about the positive. So one thing we have, so if we have some location, and we can say that I told you that if we look at this theta, okay, that theta, this theta is actually calculate using solving the formula. For example, if we have a pole somewhere here and we just want to calculate this theta, and this theta easily calculated as so from here we have theta is equal to cos of theta. Okay, and the important factor we have to know that if we come towards the real axis, we have less overshoot. So actually zeta is with formula if we look at is with the overshoot. So this means that as we coming towards the real axis, so we have less overshoot. Okay, as we go away we have more overshoot. So this is the one spec that we have. The second one is if we look at the omega n, because the point here on the j omega axis is with omega n, so this is the omega n. So if it is a semicircle, this will give us the value of omega n. So as we go in this direction, means that if we have this type of omega going in this direction, we have what you say less rise time. Okay, so if we move in that direction, we have fast response of the system or less rise time. And we have the last thing that is represented by a straight line that tells us about the settling time. As we go in this direction, we have more fast response. So the main idea is so we have we can choose specs based on settling time, rise time, and overshoot. So on base that we can choose some, for example for overshoot we choose this thing, for rise time we choose this thing, and we also choose for settling time. So we make an area here, so we want our poles to be placed in that area that can satisfy all the constraints that are specs. So if we have poles of the original system placed here, so we want it to move to this direction, so that for that reason we say that this is specs that we need to meet when we have to design a controller. We will look this in further detail when we discuss the control design. So this is the basic idea. That's why time specification is very important. So I will stop here. Thank you for listening.